So everyone, this is Wick Haxton. I'm the designated host for this week for the colloquium, and I have the honor of introducing today's Berkeley physics speaker. It's Marcelle Soares-Santos from the University of Michigan. Marcelle received her master's and her PhD degrees in astrophysics from the University of Sao Paulo, Brazil, studying respectively cosmological gravitational waves and the cosmological evolution of galaxy clusters. She finished in 2010. Her graduate career included a year as a guest scientist with Fermilab's Center for Particle Astrophysics. And after she completed her PhD, Fermilab invited her to remain as a postdoctoral researcher to continue her work on the dark energy survey, where she played a major role in the construction of the dark energy camera. She was acknowledged in 2013 as one of the DES builder team, the core members who each invested at least 2 years of effort in making the dark energy survey a success. In 2014, Marcelle was promoted to associate scientist at Fermilab, becoming a member of the Dark Energy Survey Executive Committee, as well as project lead for the DES Gravitational Waves project. That resulted in a spectacular success in 2017 when LIGO and Virgo detected gravitational waves from GW 170817, the first neutron star merger event observed. Using the dark energy camera, Michelle's team was able to observe the associated kilonova, the optical source created by the expanding radioactively powered debris from the merger. The team pinpointed the event's location and observed its evolving light curve over the next several weeks. Marcelle represented DES in the NSF press conference celebrating GW 170817, one of the real landmark events in the recent developments of multi-messenger astrophysics. In 2017, Marcelle joined Brandeis University as an assistant professor and holder of the Landsman Career Development Chair. In 2019, she became a Sloan Fellow. Earlier this year, she moved from Brandeis to join the University of Michigan, becoming a faculty member in physics. In addition to her work on DES, she is a member of the Large Synoptic Survey Telescope Dark Energy Science Team and an external partner of LIGO. So on behalf of the department, I'm delighted to welcome Marcelle to Virtual Berkeley, where today she'll tell us about cosmology in the era of multi-messenger astronomy with gravitational waves. And audience, please feel free to type in questions to the chat as the speaker proceeds, and I can interrupt and ask those if you wish, or if you want the questions asked at the end of the period, please let me know that in chat as well. Thank you. Marcelle?
Thank you. Thank you for the invitation. It's always a pleasure for me to talk about this project, which I think it's really exciting. And it's always a pleasure as well to give a talk to an audience like this. Thank you, everyone, for joining in to this virtual colloquium. Well, thanks to this great introduction, I can jump right into explaining the image that you're seeing here on the title slide. What you're seeing here is a side-by-side set of a pair of images comparing what we call the discovery image taken on the night of the merger of GW 170817, the first merger of two neutron stars ever observed. And on the other side, you see the same region of the sky observed under the same conditions merely 2 weeks later. And for the non-astronomers in the room or the virtual room, the main takeaway messages from this image, other than enjoying the beautiful image itself, is the fact that the source that we are talking about, the optical counterpart of this merger, is this little dot there that is highlighted by the crosshairs here on the left. So what you take from this is that we are talking about, if you really want to do any science with these type of events, we have the challenge of identifying a source that is faint. Take here you can imagine, even without being an astronomer here, you can imagine that we are talking about a source that is is being observed here with a 4-meter telescope on a 30-second exposure. So it's not really the faintest object out there. We are capable with this telescope to observe things that are much fainter than this, but it's not very bright either. You compare this is an object that is at 40 megaparsec, which for cosmologists is really very nearby, right? So it's a challenge to observe faint objects like this when they are short-lived as this one here. So that's the reason why this is the first time that we have ever observed them, because they are faint and short-lived, right? But it's exciting, and we really want to go after detecting these and building a program to do these detections effectively, because we can do great science with them. And again, the list of potential science investigations that you can do by studying these events is really long. If you're interested in astrophysics, etc., there's a long list of things that you can study by looking at the aftermath of the collision between these two neutron stars. But for us here today, the main point will be cosmology. That's my main motivation. So it's the topic that's the favorite for me. So I will go with that and show here the motivation for cosmology. So why bother? Why would I, knowing that we can measure the cosmological parameters, for example, what we have here in this plot is h naught, the rate of expansion of the universe today. We have several different methods of measuring this quantity with great precision. So why would we bother with a new method, for example, using these events? And the reason for that is that the more precise the measurement, the more discrepant they seem to be. And this, I'm pretty sure many of you have heard and at length discussion about this discrepancy that exists between the measurements that are made, for example, with supernova or other local observables, and the measurements that are made with a cosmic microwave background, which are based on measurements of the early universe. This plot here, although it is a few years old already, it's one of my favorite representations of the problem. So here I would ask you to concentrate, for example, on these data points here, which are obtained from supernova measurements, and compare, for example, the latest result at the time of this plot with what you would expect, for example, to see from Planck results, assuming a lambda CDM cosmology. That means assuming that the dark energy component of the universe is Einstein's cosmological constant only, right? And you can see that these results, they disagree significantly with each other. And again, this is just one plot, and you can find in the literature many different versions of this plot. And in all cases, what we see is a significant discrepancy between what you see here with supernova measurements versus what you see with the cosmic microwave background. Now, it could be that this discrepancy is caused by some systematic effects, but if not, then this can be a smoking gun of new physics. In particular, it could be the hint that we need to start to get at the bottom of what dark energy is. And one example of that is given here by these arrows at the top. That's why I like this version of this plot. So here what they did, with the authors of this paper, what they did was to compute by how much the Planck result would move to be in agreement with their result if you changed certain parameters in your cosmological model. So instead of just lambda CDM, if you allow dark energy to have an equation of state that is different from -1 by only, say, 10%, you would already improve the agreement significantly by this much. If you allow this parameter to change with time instead of being constant, you would get this much. And if you instead, you were to keep lambda, but you were to change the number of neutrinos present in the early universe, this one is the one that my colleagues in neutrino physics are usually fond of. So for example, imagine a sterile neutrino or some new particle. You would make this much of a change. So this is just a way to illustrate how exciting it is to be able to get to the bottom of the reason for this discrepancy. If it is systematic uncertainty, we want to know that, and we want to rest, knowing that we solved it. And otherwise, we also want to get to the bottom of it, because it could be the observational handle that we need to try to investigate this new physics in these parameters. So motivated by this, people all over the place have been investing in making the best measurements, controlling the systematic uncertainties in every way they can. What I'm going to talk about today is the possibility of investing, I wouldn't say instead, but in addition, investing as well in a new observable, and that would be the multi-messenger gravitational wave emitting mergers of neutron stars and black holes. And throughout this talk, I'm going to try to convince you that this is a promising approach, okay? All right, so let's go on to the next slide. Yep. And let me introduce the Dark Energy Survey, because this project, we are pursuing it in within the Dark Energy Survey collaboration using the camera that we built for the survey. So what you're seeing here on this slide is a picture, my favorite picture of the Dark Energy camera, DECam for short. So what you're seeing is a focal plane of the camera with beautiful CCDs, just the moment when we were about to ship it from Fermilab to the site in Chile to be installed on the 4-meter Blanco telescope there. This was in 2012, which now it feels like a very long time ago, when I was a postdoc working on this experiment. Since then, the DECam has been a success in the sense that we were able to pursue the entire observational program of DES, and at the same time, we made the camera is available for the community, and it's being used for other programs as well. For DES in particular, we used this camera between 2012 and 2019 to pursue what we call the wide survey, so 5,000 square degrees of sky in multiple bands. And this is with the goal of using galaxies and clusters of galaxies and their distribution in space and their shapes to measure dark energy. That's not what I'm going to talk about today. It's a topic of an entirely different colloquium. In addition to that, there were 30 square degrees in the sky that we revisited with a cadence of about one observation every week. And these observations were with the goal of doing supernova cosmology. So adding to this plot a dot that would be from supernova from DES. This is also a topic of another talk. I'm not going to explore that today. Now, what we did starting in 2015 was we added a new program, which was the follow-up observations of gravitational wave events detected by LIGO and Virgo. And that's the DESGW program, which is the topic of today's colloquium. There was also a spin-off of that, which is a follow-up of certain neutrino events from IceCube, which also I'm not going to talk about today. That's a smaller, much smaller observational program. So as I said, the DES main program, wide and supernova observations, they ended in 2019. But as you know, was that a question?
No, I don't think so.
Okay. All right. So yeah, so what I was saying is that the GW program continued until 2020. We finished the observations just in March of this year. And that's because our program was in sync, of course, with the operations of the gravitational wave detectors. And that's what I'm going to talk about today. Now, before I dive into that, let me use this to advertise some of the results from the DES survey using the galaxies and a clustering of galaxies. What you're seeing here is just one plot out of several papers we published a while ago. New results are coming soon. They are going to be announced. Our target date for announcing the new results is in January of this coming year. But what you see here is the result of the previous round that covered the first year of observation, so the DESY1 results. And what we are seeing here is just one plot to illustrate. Here we have omega m, the fraction of the matter energy content in the form of matter, the content of the universe in the form of matter, sorry. And here S8, which is a quantity that is have to do with the amount of clustering of galaxy. And what I want to, my insistence in showing this plot here is to show that here again, we have a little bit of tension between the DES results, which is this blob here, 1 sigma, 2 sigma, and what would be the Planck result here in green. Again, this is not something I would write home about in itself, but it is useful to illustrate that everywhere in the parameter space of cosmology that we look, the more precise the measurements we make, the more these tensions seem to be creeping in, and they are growing instead of going away, which is another indication that if this is caused by some systematic uncertainty, it has to be a very peculiar combination of systematic uncertainties creeping in different types of observables, because this is not supernova. This is observations done with using only the galaxies. And so that is another way to say that it is really important for us to get to the bottom of what's going on in this discrepancy between our measurements and the cosmic microwave background. All right, so I hope you're convinced that we want to do this. Now, let's dive into how can gravitational waves help us? So the name of the game here is standard sirens. And what are standard sirens, right? I like to show this paper from the 80s, where it was one of the first papers describing the idea of measuring the rate of expansion of the universe using gravitational wave observations, observations of gravitational wave events. I don't expect you to read all of this. I just like to advertise this because I keep saying that when I grow up, I want to be able to write papers like this. Very short, 3 pages, no figures, just a couple of equations and a hell of an impact, right? So what did Schutz do in this paper? He described how you could obtain the amplitude. So this is an excerpt from the paper. One of the equations here in equation 1, you have a calculation just using the quadrupole formula from Einstein's general relativity for a merger of 2 objects of mass m1, m2, so that the total mass is m sub t, and this is the reduced mass mu. The amplitude of the gravitational waves emitted by this system as it merges is proportional to a combination of these masses here to some power, okay? Now, what is the key feature here is that the rate of change in frequency as the orbits decay and the system collapses also depends on this combination of masses. And more than that, the dependency is exactly the same with the power, the inverse power here. So the key here is that if you can build a detector capable of observing these events, and you can measure the rate of change in frequency of the waves in the last few seconds before the merger, you can determine, modulo this combination of masses, the amplitude, intrinsic amplitude of the waves. And you can compare that with the observed amplitude on your detector, and boom, you have a distance measurement, a luminosity distance measurement for that event. So the idea is very simple. And as you may have noticed, it did not require any type of calibration of the source based on distance ladder, et cetera, which usually adds a number of systematic uncertainties. It's not that this is free from systematic uncertainties, but it's just that the set of uncertainties will be different. And that will be very helpful if we can make measurements with precision high enough to compare with the plot that I showed earlier. So with this in mind, we were not the first group of people to think about that. A number of people have been thinking and looking forward to the day when gravitational wave detectors will be sensitive enough to detect things to allow this type of measurement. And well, in 2015, the LIGO and Virgo collaborations made an announcement saying that, well, we are going to start observing. Actually, in 2014, they made the call saying that they were going to start observing in 2015, and that they would be sensitive enough to perhaps make a detection. So at that point, we decided, we in DES, we decided that it was a good idea to attempt to do that. And this plot that you're seeing here shows, quantifies the size of the challenge that we were facing at the time. This plot is a little bit old, but the point here is still the same. What you see in the y-axis in both sides is the size of the area in the sky. On this side here is considering that you have only the 2 LIGO detectors, so you have to triangulate only with these 2 detectors. And here is when you add Virgo. And on the x-axis is the percent confidence, localization confidence enclosed in that area. So what you see is that even if you're with 3 detectors, these areas are tens of square degrees. To get something like, say, 90% confidence, you would need something that would be approximately 60 square degrees for a typical event. So this is for a series of simulated events, just to illustrate. So 60 square degrees is a lot of sky. The dark energy camera, which is a camera with one of the widest field of view ever put on a telescope of this size, it has 3 square degree field of view. So this gives you an idea, right? So this is a large area, but again, it's 3 square degrees that we have available with DECam. So the thought at the time was that if anyone can do this, it's us, because DECam is really an instrument that is made for this type of wide area searches, right? So once we convinced ourselves that the areas that we had to search were large but doable, we decided to adapt our image processing pipeline for the challenge, right? So here is a cartoon description of how that works. When the merger happens, the LIGO and Virgo detectors will trigger a detection saying, we saw something somewhere in the sky. We have a piece of code that we call the main injector that takes that sky map that is not very well localized, but that gives us a region in the sky, creates an observing plan and sends that to the mountaintop. The observations happen, and then once the images come in, what we do is we process them and we compare with pre-existing images with the same region in the sky. This generates a list of candidates, point sources, that are transient point sources that are candidates. And we then vet and those candidates to produce a list that goes into a public website. So this entire process here, from the moment we get the raw image to the moment we get the list of candidates, we have to do that relatively quick if we want to allow other telescopes, for example, to do follow-up observations to confirm those candidates and reject false positives, and also to enable taking a spectrum to study the system in detail and so on. And this is showing the typical time that it takes with our system to get that done, which is a great success. So I will walk you through this in the one successful case we've had so far, which was 2017 0817. So you all have heard probably about the story of the this great event. The distance is 40 megaparsec, and it happened on August 17, 2017. We were not the only ones looking, so I don't expect you to read all of this, but this list is not a list of people, but a list of collaborations that were involved in pursuing follow-up observations of these LIGO events. And again, if there are collider physicists in the room, for collider people, 1,000 authors in a paper is nothing new, right? But in our field, this is still something relatively new. I've never been in a paper with this many authors before, and it was a great adventure and to work on this. So what were we all looking at, right? So what is the mechanism that generates the electromagnetic signature of a merger of two neutron stars or a binary neutron star system? What you see here is a cartoon illustration of those two types of emission. This type here are what we call relativistic outflows. So this basically is non-thermal beamed emission. Because of the very strong magnetic field of this system, you will have a beamed emission that will be bright in gamma ray, X-ray, and radio. In particular, the X-ray and radio emission will happen once the jet coming out of the system reaches the interstellar medium. There are many papers out there with detailed models and so on for this emission and how it happens. And I suggest people, these are just two of them, but there are many other papers out there with this description. Well, this is great, but this is not good for us because these wavelengths are not the wavelengths that our cameras are sensitive to. There's also emission that is subrelativistic at, let's say, up to 30% of speed of light. This is thermal, and it's more or less isotropic, which is great because in this case here, you have to be lucky enough to have the beam be pointed in your direction. Here, it doesn't matter where you're looking at. It could be that you get different emission in terms of redder or bluer emission, depending on the viewing angle, but you will get something at any angle that you observe. And this will be bright in wavelengths going from near here UV to near infrared observations, which is great because DECam is sensitive in this wavelength regime. So this is what we were looking for in emission like this. The relevant parameters that will will determine how bright and how long the electromagnetic emission will last are the amount of mass ejected, which is about 1% of the solar mass, the velocity of the ejected. If it's too fast, the bubble of hot material will expand too quickly and it will cool down too quickly. And in the opposite case, it stays hot a little bit longer, right? So that's the second parameter. And the third parameter that I didn't list here is the opacity. Depending on the opacity of the material that is ejected, you could have outflow brighter and also different wavelengths here. Now, in the case of the W170817, it was beautiful because there was evidence for both mechanisms. So what you're seeing here, and again, this probably people have seen before, in the middle, you see the gravitational wave signal with the chirp. So this is frequency, this is time. And so here you're seeing the strength of the signal going up. This is the time of merger, 0.0. And what you're seeing in the histograms here is the gamma ray data from two satellites that were able to see emission 2 seconds afterwards. So if we had only this signal here, this would have already been a spectacular multi-messenger event. I would not be so happy because I don't work from these wavelengths, but it would already be spectacular. But there was more. GW170817 was really a big gift for all of us. Once the event happened, the first thing that everybody working on optical wavelengths was doing was to try to scan the region of the sky looking for the counterpart. And what you're seeing here is projected in this projection here in the sky, what that region looked like. This is about 60 square degrees. Remember that I said that for the average event, we had something like 55 square degrees typically for 90% confidence. This one was similar to that, okay? And here is a zoomed in version of this elliptical region with dots here representing galaxies that are inside this volume. This is done by the SWOPE team and published in this paper here. Their telescope is a small field of view telescope. So what they did was make a list of galaxies and point at individual galaxies one by one like this. Okay. Now, in our case, our camera has a 3 square degree field of view. So it doesn't really make sense for us to go hunting in a galaxy by galaxy basis. So what we did was instead we covered the entire, like here again, 50% and 90% region are the white contours. And the red hexes represent the footprint of our camera in the sky. So we covered the entire thing. And because our camera is fast, we were able to cover it multiple times. So we covered it in different filters, and we also covered it multiple times to look deep. We had a team of people at the mountaintop doing observations. This is Jenna Marshall, one of our group members, and also people at Fermilab in the remote observing station there, and we were in communication and trying to process the image on the fly. It was really an amazing, exciting time. But remember that I mentioned that this object was at a distance of 40 megaparsec. So this is really, really nearby. So if the models were correct, we expected that the source at this distance would be bright enough to be visible in the raw images even before processing. So what we did, in addition to having our system, the pipeline that I described in my cartoon earlier, we had it run, but at the same time, we had a teams of people eyeballing the images as they came, because we maybe would get lucky and make a detection in the raw images themselves. And behold, we did exactly that. So shortly after taking our last exposure, one of our colleagues was eyeballing the images, did see it, and sent this email to our mailing list with his discovery. This, I think, was the most exciting time ever. I cannot begin to describe how awesome this was. So we had a detection, and we were really excited. And then what now? What is the protocol, right? So the protocol here was to communicate via the GCN network. Basically, you write an email to this network saying that you see a candidate of this and this coordinates and so on. So I'm there literally typing as fast as I can the coordinates and the information about this object, when I see an email pop up, and guess who? Well, members of the SWOPE team had seen it too, and they typed faster than I did. So they claimed discovery mirror and independently, our teams claimed discovery of the same object. So here is for completeness here. I'm showing the image from their discovery paper. As you can see, maybe it doesn't. Okay, I am probably not impartial enough to say, but I would say that our image looks better. But you can see the source is clearly there, and they saw it too. So this was exciting and humbling at the same time. This is a 1 meter telescope with a narrow field of view. Again, the key here was that this object was very close and very well localized. So that means that a small number of galaxies for them to look at. And this object was, I think, in galaxy number 9 of their sequence. So it was really good, and so on. Our teams were not the only ones. There were several others that independently, as you saw the list, right? There were many teams looking at this, looking for it, and several of them saw it independently and reported the discovery within minutes from each other. So it was clear that we were looking at the right place at the right time, and this was very exciting. Now, after the excitement of the moment is over and you start thinking a little bit more about it, you may ask yourself the following questions. One of them is, are you sure that this is the thing? Are you sure it's not some other transient that happens to be at a galaxy at 40 megaparsec? That's one question. And the second one is, can you do this again? It looks like it was too easy. 6 different groups were able to look at this to make a discovery independently. Could you do this again for a typical event that is much further away, say at 100 megaparsec or 120 megaparsec, which is a typical distance that will be in the upcoming runs. So in our paper, where we reported the discovery of GW170817 with DECam, what we did was to try to answer these questions. We allowed our system to go through the processing of everything to the end, and we introduced simulated events, and we did all of the analysis. I can go in detail more if people want to ask about this, but basically what I'm saying here is that after running all of that and pretend you didn't see the object by eye, right, and just let the system go through, we find that our analysis returns one object, and that is exactly the same that we discovered by eye. So this is very reassuring. It shows that the system that we put in place works. It confirms as well that this counterpart is the optical counterpart of that event, and builds a lot of confidence that not only we're looking at the right object, but also that we can do this again, and that we can start dreaming of making a program to discover many objects like GW170817 in the future. Now, what about cosmology? That was the motivation, wasn't it? So this is the measurement. This was in a paper led by the LIGO collaboration and published also in 2017. What you see here is the posterior distribution of the H0 measurement using that one event. Basically, what you do is a Hubble diagram. Y-axis is a distance taken from the gravitational wave event, and in the x-axis is the redshift that you obtain using the redshift of the galaxy that you just identified. And with only one event, of course, we are not in the land of precision cosmology here, right? So you can see that this distribution is very broad, and it's in agreement with both Planck and the supernova measurements as expected. And but it's interesting because this is only one event, and you can ask yourself how many events do we need to accumulate in order to get the precision measurement. And I'll get to that in this talk later. Now, H0 is only one cosmological parameter. If you really want to get to the bottom of what dark energy is and so on, what we need to do is perform analysis where we measure multiple of these parameters at the same time. That's the type of analysis that DES does. And the plot that I showed earlier from the DES Y1 was, I think I showed this panel here, which was sigma S8 and omega m, right? But it's a one of several panels in a multi-dimensional parameter space. What we want is to see by how much this parameter space changes when we introduce gravitational wave events. And so this is what we did here. This was done here with my group. Was just to play with that possibility with a few simulated events. We throw them in and ask the question, by how much would this parameter space change? And what you see in red is the new contours, assuming the same DES data, but just adding 8 GW170817 like events. So this is already giving you a hint that we are not talking here of accumulating necessarily thousands or tens of thousands of events in order to make an impact. We can already make an impact with something like a dozen or a couple of dozen of events in this parameter space. And this is also very exciting because if you're like me, anxious to see results coming up soon, this I think bodes well for that, right? Now, here's another way of looking at the prospects for this science. What we have here, I made this plot in the following way. In the y-axis is expected number of BNS events to be seen by the gravitational wave detectors, assuming a certain evolution in their sensitivity. And basically the detectors get better and they run for longer and so on. So you accumulate more and more events. We are here today with only one event detected, but the idea is that we would accumulate more and more over time. And what I did here in the bottom part of this panel was a scale by just the square root of n of the uncertainty in H0 that we obtained with GW170817 to show how quickly we would progress towards a level of precision that we need to distinguish between the CMB and the supernova results. Okay, and what really for me is really exciting is that when you look at the x-axis, this is time, right? We're not talking about decades here, right? This time range is, as I say, is just a typical lifetime of a graduate student. So this is really exciting because it means that in our scientific lifetimes, we are going to see a number of events that is suitable for this program. It's not, something hypothetical. The potential is there. Now, in order for us to follow this path and be able to extract the science that we're interested in, we really need to go after this counterpart because, we cannot make the measurement following this curve if we cannot detect those counterparts, okay? So here, the timeline that I put in is an approximate timeline showing that, again, DES is pretty much done. We are going to analyze the data that we obtained with so far and produce more papers, etc. But no new data will come from the DES program itself, right? But we have DESI and we have LSST and the LIGO detectors, which are now in shutdown for upgrades. They're going to come back with greater sensitivity. So that's how this curve continues to climb like that, right? And the expected date to start the next run is around 2022. Which is about the same time as DESI will be running, LSST will be running. It will be a very exciting time for, and so again, if I would be a graduate student, I would be with an eye on this type of experiment because the wealth of data will be fantastic. So what about black holes? You probably have heard that so far, while we have seen only a couple of binary neutron star mergers, we have seen about a factor of 50 times more binary black hole mergers. And the reason for that has to do with the fact that being more massive, they are louder in the gravitational wave detectors. And that means that they can be seen at a greater volume. So you see more of them. So what we are doing with those events is that we have been searching for electromagnetic counterparts of those events as well. The theoretical motivation is not as strong as it is for binary neutron stars. So maybe there are no counterparts, but if they are there, we are looking for them. So what I'm showing here is plots of the sky localization of 2 of those events, where we mapped out part of the localization area. In this case here, we mapped out the entire localization area. And so far, we have not found any counterpart, but we keep looking to trying to either make a discovery or place meaningful limits that can exclude some of these theoretical scenarios that predict emission. Now, you may ask the question, if these binary black hole mergers are really too dark to be detected or completely dark, can we still do cosmology? And the answer is yes, as it turns out. And this plot here I made based purely on simulations to try to illustrate how this works. Basically, the idea here is that because the galaxies are clustered in the sky, we actually get each galaxy along the line of sight of the event would correspond to a different value of H0 because each galaxy has a different redshift if they were the host, right? So while you don't know exactly which galaxy is the host, you can build a posterior distribution that looks wavy like this, where each galaxy is contributing to a different value of H0, and clumps of galaxies work together to make bumps in this posterior distribution here. Now, with only one event, and here the gray lines are each gray line is for an individual event simulated, and the colorful lines are some events that I just highlighted for illustration purposes. So if you had only one event, say this one in red, you probably would think that H naught is like 50. If you had only the orange one, you would think that maybe it's here or here. But what happens is that once you combine all of these events, these other bumps, they will wash themselves out, and you will converge into a measurement of a true value of H naught, which is 70 in this case of the simulation here. And how many events do you need to converge? Well, it depends on the size of the distance uncertainty. So each panel here has a different value of uncertainty in distance. And it also depends on the uncertainty in redshift. Those two things that will work against you in the measurement. But with enough events, in this case here, we have 100 events in each of these panels. We can converge into an appropriate, measurement if we get enough events. So with this motivation, we decided to go after one of the BBH events, and this is GW170814. So this was just a few days before the big BNS event came. We had this beautiful black hole merger that was in the middle of the DES area in the sky. So what you're seeing here is the 50% and 90% contour for that event. And the map is a distribution of galaxies seen by DES in this region. Here's the same region, but now you're seeing the redshift cone, and again, the distribution of galaxies. And you see the clumps that I was talking about before. They, of course, is mirrored out because DES is not a spectroscopic survey, but you can see them there. So you could see that different values of H naught would come out of this. So we decided to apply this idea to this data. And here's the result. In red, you can see the posterior distribution that we obtained. For comparison, this is the posterior distribution that was from GW170817. As you can see, this is much broader, of course, because you're not pinpointing the counterpart anymore. But there is a distribution that is sensible there. And this bodes well because, well, this is only the first of many hundreds of events to be detected by LIGO and Virgo, and also future detectors that will come. So this is very exciting because it means that we don't have to throw away the black hole mergers. We can use them too. And more than that, we can use them in combination with the galaxies that we detect from DES, which we're doing it anyway. So it's really exciting because most of the time when you have a new way to observe or to do a measurement, you usually need to go out there and build an instrument and do, spend millions of dollars to get your instrument on the sky and so on before you can actually make a measurement. In this case, we already have the data. We already have the galaxies. All we need are the gravitational events. So that was really exciting, but you notice that I'm talking about events that are all from 2017 and so on. So those events are from the first two campaigns of observations that LIGO and Virgo collaboration did. So after a pause of about a year, they came back in 2019 with a new year-long observing campaign, okay? And this was the third, what we call the 03, observing campaign number 3. And during that campaign, we saw explosion in the number of events, over 50 good candidate events detected by the LIGO-Virgo collaboration. About a dozen of those with at least one neutron star. And of those, 3 were pursued by our team with the direct energy camera. The growth team, which is another team that also uses DECam, also did follow-up observations of some of these events. What I'm going to talk about here is I'm going to talk about 2 events from that campaign. One is 1905-10, so an event from May, and the other one is an event from August, okay? And why are these 2 events special? Well, this one was a neutron star event, the significance was not great, and the localization area was not great either. So we didn't invest much time on it. But I'll talk about what we could do, what we did in the search, and what did we learn. And this one is the most exciting event from this batch, because this was a merger with a big asymmetry in the masses, which indicates that one of the two components is probably a neutron star, and the other component is probably a black hole. And the distance, as you can see, is several times the distance of GW17 or 817. So really further away, which means a lot more, a lot fainter. Flux goes down distance squared, so you can imagine how much fainter. And we invested 5 nights of observations into this event. And we covered the 90% localization area, which was 23 square degrees. So it was better localized in a typical event, but still far away. So what did we get from those events? Well, here's the sky maps showing the area that we covered, and this is the result. Well, we don't know if these are actually bright standard sirens, in the sense that if there was really emission there. Of course, we didn't find any. But so what we did here is put limits on this parameter space of ejected mass, velocity of the ejected, and opacity. As I said, these are the 3 parameters that matter for this subrelativistic emission. Here is where, if this event would be GW17 or 817 like, with the same mass ejected, etc., same parameters, we would have seen it. But we did not, which means that either this event could be with a smaller amount of mass ejected, or different opacity or something like that. But we did not detect, and we report the results of the search and the interpretation in this paper, which is accepted in the Astrophysical Journal and will be published soon. I encourage people to go and have a look. We did a similar analysis for the mixed and SPH event, and that one, as I said, is even further out. And again, this is if it would be GW17 or 817 like, it would be in this region. And we did not make a detection either. And we covered most of the parameter space very well, but you can see there's a lot of area here that we did not cover, and we would like to do better next time with better searches. This one is reported in this paper, which was it is also in Astrophysical Journal publication. Now, finally, what about cosmology once again, right? What we did here is, with these events from 2019, we updated the result of the cosmology using these events that don't have a counterpart. We use them as if they were black hole merger events, right? And what we obtained is this red contour here, which is combining all of them together. Again, we are not yet able to distinguish between supernova and CMB results, but this is an improvement over the early first results. And these are still early days of this type of science. So we think we are on the right track, and that soon we will actually reach the precision that we need to make this distinction. The result is published in this paper that I also encourage people to look into, where we describe the analysis in detail. So in summary, our team is leading a search and discovery program for EM counterparts of gravitational wave events. We participated in the discovery of the spectacular GW17 or 817 recently, and since then we are improving our searches and using these events for cosmology. We did the first measurement using a black hole merger, and we call those events dark sirens because they don't have EM counterparts. And in the third observing campaign, we did, in addition to improve the searches, including simulations and so on, we also started to use dark sirens combined with bright sirens to try to get to cosmology. Thank you. I'll take questions.
Well, thank you, Marcelle. This was really entertaining. I guess it'd be easiest to ask questions by raising your hand. So I'll watch for hands to raise. And the first one comes from Christine.
Hi, thank you for the talk. I have two questions. So one, could you talk a little bit about the priors you used to do the measurements with GW 170814, like what kind of priors you're placing on the analysis?
We use a flat prior on H0, and that's the only real prior that we use there.
Okay. And there was the recent Graham et al. Paper for GW 190521 that had a candidate electromagnetic counterpart to a binary black hole. Do you know if there have been any standard siren measurements with that?
No, I think that not that I'm aware of. We didn't pursue that ourselves, and I don't think there's a measurement there. But
okay, thank you.
And Sherwood?
Hi, thanks for the great talk. I had a little bit of a more basic question on the cosmology. So if I understand correctly, the measurements of the cosmology parameters come from galaxy clustering, supernovae, and the cosmic microwave background. Is that right?
yeah, so you're talking about the traditional measurements. That,
yeah, just overview.
Yeah, yeah.
And
yeah,
so
those are some of the methods that that we traditionally use. Yeah.
Okay, so then the question is there enough data to significantly determine whether there are trends in, like, because some of these things come from different redshifts. If there are trends in the parameters, is a function of redshift as opposed to some inherent systematics.
So you were talking about, like, you're perhaps making tomographic measurements or making measurements in different bins of redshift and comparing and so on.
Right.
Yeah. So we look into that, and we think we are doing a good enough job that you know, if there are systematic uncertainties playing a role, it's not obvious that they are, you know, they're not showing up when you do this type of cross check, you know. So we do a series of cross checks of that type, and things seem to be consistent. So if it's an effect like that, it's something very subtle, or something where you have perhaps multiple effects conspiring in a, you know, in a weird way, and it's not clear. But again, we have to say that in all of these measurements, all of these observables, they are in a systematics limited regime. So these measurements are very hard. So I wouldn't rule out the fact that, you know, maybe we did miss something, but we are working really hard to avoid that.
All right, thanks so much.
And Chris?
Thanks for the very clear talk. I had a question about the dark sirens. So you, in your graph, you showed that as LIGO and Virgo get more sensitive, you will be able to get more sources. But on the other hand, that means you'll be going out deeper, and you will have more galaxies that you have to add to your graph. I'm just wondering how those two things play off against each other.
Thank you. That's a very good question. So it's true, you see more volume when you observe further out. But the key thing of, I'll try to, yeah, here. Okay, so here, what you're seeing is in the Z direction, the region in the sky where this event is localized, right? And here, what you see in white is the minimum and maximum values in redshift that you would be for, here is H0 of, you know, 50 and 90. So those, that my prior, no, not 90, sorry. This was the prior I used there. Let me, it is better. Yeah, here. The prior is actually between 20 and 140, okay? So, so what it means is that you're going to see further out, But you can imagine that this will be a box of a given volume that is going to be further out. So you're not necessarily going to get more galaxies in that volume if the uncertainty in distance is small enough. You know what I mean? So the key thing is the size of the uncertainty in distance for each individual event. And then the second one is what is the uncertainty in the redshifts of each individual galaxy.
Okay, thank you.
All right.
And Hitoshi.
Sort of follow-up question on Chris. So now the Kagra is sort of ready to go, and once they get up to the kind of sensitivity that's needed for this, how much better would be pointing?
Oh, that is a wonderful question. Thank you. So I think the most exciting thing about the Kagra detector coming online, or at least for me, is the fact that the sensitivity of Kagra is closer to, or perhaps even when it's at design sensitivity, will be even better than the LIGO sensitivity today. So they will be better matched in sensitivity than Virgo. So Virgo has lower sensitivity, right, than Virgo. So the fraction of events that have the contribution of the 3 detectors is small. So usually when we do the simulations and we see the effect of adding Kagra, the effect is huge, but in particular, it's huge in the sense that more events will have 3 detectors, and so more events will be as well localized as GW170817. That is the key thing. And so it means that you can climb faster on that number of events that you follow up and so on, because you can find them better.
Oh, that sounds great.
Yeah, that is really exciting. I'm really looking forward. I'm not certain about what is the time frame for Kagra to reach those levels of sensitivity, but I'm really looking forward to that. Yeah.
All right. Thank you, Marcelle.
Marcelle, I see no more questions. So let me just conclude by thanking you for the wonderful talk. And I know it's kind of late for you too. So we really appreciate the fact that you battled the time zones difference as well. So thanks so much.
Thank you. Thank you for the invitation, and good night, everyone. Bye-bye.
Good night.